Welcome back to Cougar Chem Tutoring. I'm Austin and I'll be running through part 1 of problem set 9, periodic table and trends. Alright, so what is the difference between a group and a period on the periodic table? The easiest way to think about this is groups are columns, okay, and periods are rows. Now the actual thing that differentiates both of them is that groups are specifically elements that share the same number of valence electrons. Okay. Now what that does is having the same number of valence electrons actually gives you very similar properties. So they have similar properties and they react the same. So sometimes we call these families. Families because they're very similar. They have very similar properties. They react a lot of the same and have even some of the same physical properties as well. Periods, on the other hand, although two elements can be in the same period, they don't necessarily have the same properties, but they always have the same energy level. So same energy level, particularly the end shell energy level categorization. Okay, so those are the main differences. Periods, you can just think of the period as a row and that they correspond to remember, these periods correspond to certain end shells. So the first period here is n equals 1, n equals 2, n equals 3, and so on and so forth in the periodic table. And groups are just elements that are in the same group or the same family that share same number of valence electrons and by default similar properties. Okay, 1b. The periodic table can be divided into roughly 4 blocks according to the type of subshell being filled. State the subshell being filled in each of these blocks. All right, so hopefully you kind of understood from our last video when we were doing electron configurations that there were these 4 blocks that we used to designate where the electrons were going. So here we've got the S block right here. I'll write the S right here. This is just the one orbital, right, in the S orbital for each corresponding end shell. Then we have the P block over here, P block. This is where we have 3 p orbitals that we can fill in there. Then we have a D block, which is where we fill in 10 d or 5d orbitals, but 10 electrons. Okay, and then this last group down here is what we call the F group. Okay, the F group. I'll just put F over here. Okay, so those are the 4 blocks of the periodic table. And how we this is actually how we keep track of filling in electrons when we're doing electron configurations. Right, so 2a says there are also different families of elements in the periodic table. Listed transition metal and alkali metal, halogen, noble gas, or alkaline earth metal, nonmetal, lanthanide, actinide, and metalloid in that order. Okay, so let's start with the transition metal. Okay, where are the transition metals? The transition metals are this huge D block. That's the entire D block is full of transition metals. Okay, so I'll just say let's go with cobalt on this one. Cobalt. Okay. So that's one transition metal. Okay, now an alkali metal comes from group 1. So I'm going to put group, I'll just put G1, okay, G1. And those are group 1 metals, and that can be lithium, sodium, potassium, so I'm just going to put lithium here. Okay, halogens come from group 17 right over here, so I'm going to put group 17. So I'm going to put fluorine, okay, it could have been chlorine, bromine, or iodine. Okay, a noble gas, hopefully you know what this one is. These guys are the very end here, right here, with the full octet. They don't have any properties. They don't really do much. They kind of just exist. And so let's go ahead and put argon there. Alkaline earth metal. These are just to the right of group 1 alkali metals. These are group 2 metals. Okay, and then I'll just put beryllium right there. All right, a nonmetal. Nonmetals are kind of funky. There's only kind of this weird group of them over here, but we use them a ton. In fact, they make up most of life and what we breathe even too. So that group of blue elements right there are what we call the nonmetals. You'll notice that it's noted with this color code down here. Those are the main nonmetals. There are others that are like the parts of the halogens that are also considered nonmetals as well. But for now, we'll just go ahead and put carbon there. All right, a lanthanide. A lanthanide comes from the lanthanide group right here in the F block on the top row. So we can just put lanthanum. All right, and actinide. Actinide is the second row on the F block, and we'll just say let's say uranium. All right, and then lastly we have what's called a metalloid. Metalloids are also known as semimetals. Okay, so metalloids are the same as semimetals. They kind of act as both a metal and a nonmetal, depending on the certain cases. Okay, so it's always going to be the metalloids are always going to be in this staircase of green elements that you see here. It's kind of a funky area. but that's kind of it's kind of just how we have to designate which ones act as both metals and semi and non-metals. So I'm just going to put, let's say, boron. Boron. All right. Okay. Letter B says, in which set of elements on the periodic table do the D or are the D orbitals being filled? Okay, remember we said this is the D block, and what did we call this whole block right here? That's the transition metals. Okay, so be familiar with the families and groups on the periodic table and where to find each, and not necessarily, you don't have to know the properties, but you should know their valence, number of valence electrons for each one. All right, size, ionization energy, and electron affinity are all properties that show definite trends across a periodic table. Describe the trends for each of these properties going down a group and across a period. Okay, so I'm going to show it all going one direction, even though we're going to be talking about going down a group. I'm going to go show it as going up a group, and we'll explain why that makes sense also going for going down a group. So across this way, we have increasing. This is increasing ionization energy and electron affinity. Oops. Okay. And I'll try to explain what these both are and why they are the way they are here in a minute. Okay. And then by default, or by contrast, we've got decreasing size. Decreasing size. Okay. Now going up, we got increasing both again. So increasing IE and EA, and then again decreasing size. Okay, size you may see as atomic radius. So I'll just put radius here, atomic radii. Okay, just the size of the elements that we're talking about with valence electrons. Okay, so let's talk about what these are first, really quick. So ionization energy is the energy required to eject an electron. Okay, eject an electron from the atom. Okay, so taking off an electron. And so we're always going to need to be putting energy into it. So what that means is, as we're going to the right on the periodic table this way, it's going to take more and more energy to take off an electron. Okay, or as we go up, same idea. It's going to take more and more energy to take off an electron. Electron affinity has to do with the affinity of an atom to accept an electron, right? If I have an affinity for something, like say I have an affinity for food, right? That means I like food. So electron affinity has to do with the atom liking electrons and wanting to take one on to itself. And what it really is, what we're really measuring here is the energy released when we add the electron. Okay. That's what that is measuring. And the more negative you get, so the more negative electron affinity you get, that means the more energy you are releasing. And that means the more electron affinity something has. So you'll actually see this increasing in negative values. So you'll see kind of like high negative values over here and then low over here. Okay. All right, and then size is literally just the size of the radius, and we'll actually kind of get to that here in part B. So explain the reason for the change in atomic radii across a period, as well as down a group. And it all has to do with this concept called effective nuclear charge. Effective nuclear charge, and you are going to want to know this concept really well, okay, nuclear charge. And you'll see this written as ZeFF sub ZeFF, okay? And what it is it's essentially the attraction, or the amount, let's say the strength of the attraction, between the nucleus and the valence electrons. Okay, valence electrons. Okay, so the outermost electrons, outermost. So how much pull does this nucleus feel on, let's say if we have an N equals 3 electron, how much pull does it feel when it's trying to pull on that electron? Remember, the nucleus is positively charged with protons, and then it's trying to pull on this negatively charged electron. And depending on how many layers of electrons separate them and how far away it is, then it's going to determine how hard it is or how strong this attraction is. Now, you can imagine that if this attraction is really strong, that it's going to be harder to take away the electron, right? And that's the whole concept behind ionization energy, is that when we're trying to take away an electron, if we have a strong effective nuclear charge, if it's really high, it's harder to take away. So that's why we increase our ionization energy as we go up. Because imagine, let's see why fluorine would say have more than chlorine. Okay, So fluorine has, 9 protons. Okay, 9 protons. I'm not going to write all 9, but just pretend we got 9 right there. Okay. And it's got this only one s, or the n equals 1 shell and the n equals 2 shell, and it's pulling on 8 or 7 electrons here around itself. Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, and it's pulling on that. Okay, now it has a relatively strong grip. It's one of the most it's one of the elements with one of the strongest effective nuclear charges. Okay, so it's pulling on each of these electrons in the valence shell pretty well. Now, if we compare that to chlorine, okay, chlorine does have more protons, right? I'm going to draw more protons for chlorine. It's got what 17 as opposed to 9. Okay, so we've got this huge nucleus, but now not only do we have this layer of N1 shell and N2, we now add another N3, and actually adding that N3 makes a huge difference. So pulling on this on these outermost valence electrons is even harder, not only because they're now further apart, or further away from the nucleus, but now they are being shielded by other electrons that are in the way, right? These electrons in these other end shells, which are also negatively charged, are repelling those, or these electrons are repelling those other valence electrons outward, okay? And so what's happening is the strength between the nucleus and one of these electrons is now decreased. Yes, we've increased the number of protons, but the problem is now we are we're farther away and we're getting repelled more. So that's why fluorine has a higher effective nuclear charge, or a stronger effective nuclear charge, than chlorine. Okay, and fluorine, we could go into why fluorine has a stronger effective nuclear charge than oxygen. It just has to do with the number of protons in the nucleus. Okay, so it would make it harder for us to knock off an electron off of fluorine than it would for chlorine or for oxygen, because of this unique effective nuclear charge, this really strong effective nuclear charge that fluorine has. Okay, and we can the idea behind radius is the same idea. Okay, so here they're asking why the change in atomic radius changes as you go down a group. The reason is because if we have fluorine is going to be smaller than chlorine because it's able to pull things in tighter, right? We said that it's pulling things in tighter, so it's going to look smaller, right? And it's got less end shells, it's got less shielding, electron shielding, making this look bigger. But chlorine, on the other hand, not only does it have more shielding around it to make it the layers make it bigger, but these outer electrons are even being pushed further away from the nucleus because of that repulsion of the lower end shells, okay? So chlorine is going to be bigger for that reason. And so the weaker, that's why the trend is actually the opposite in terms of radius, okay? You'll decrease in radius as you increase in effective nuclear charge. So let me just put that here. As Z effective increases, that equals decrease in size, which is an increase in ionization energy and electron affinity. Okay, and electron affinity is just, remember, the energy released when we add an electron. And if the higher we go, let's say we were trying to add an electron to fluorine, okay, that could release some of the tension that's felt in this effective nuclear charge. It would make it actually, as adding this would actually make this a little bigger, because it would weaken, it would spread out that effective nuclear charge amongst the other electrons that are there, and now a new electron. Okay, so electron affinity is also the reason that is also caused by the effective nuclear charge trend that we see in these periodic trends due to effective nuclear charge. Okay, so let's see if we can answer this part here. It says, identify each statement as true or false. If false, rewrite the statement so it is true. Number 1, ionization energies are always positive. Okay, meaning if they're positive, that means we always have to put energy into it to happen. And that's true, right? We never get energy back. It always requires energy to knock off that electron because we're trying to break the effective nuclear charge attraction. So this is going to be true. True. Okay. Number 2 said silicon has a larger first ionization energy than carbon. Well, here's silicon and here's carbon. If we follow the trend, silicon should have a lower first ionization energy than carbon, right? So this is actually false, and I'm just going to put vice versa for simplicity, okay? Because it should be carbon has a larger one than silicon. Okay, number 3, it says the second ionization energy of an atom is always lower than its first ionization energy. It's actually false, right? It's actually the exact opposite. It's always going to be always bigger. Because if you can imagine, let's go back to the fluorine example, or let's use a new one. Let's say we've got neon gas. neon gas, and we turn it into, we knock off, we put some heat into it through some ionization energy, and we turn it into neon plus. Now, even though it's got the, let's say we've got the nucleus right here, now we've got these outermost valence electrons, but now we're missing one. And so now we have the same strength that it had before, but now it's spread amongst even fewer electrons. And so it's pulling those electrons even further inwards. Okay, so it pulls it tight. So this would actually end up being smaller. But it would also make it harder to grab another one of these. So that's why the second ionization energy is always higher or larger than the first. Is because once you lose the first, you've now condensed your effective nuclear charge into fewer electrons, and so it's pulling things in tighter. Okay, when things are charged, like positive or negative, it's actually slightly destabilizing. Things don't like to, elements do not like to be charged. In fact, they'll try to be as neutral as possible. So it will more likely, it's actually highly likely to get a negative charge than to let you take away another negative to become even more positive because of this effective nuclear charge. Okay, so false, and we would say here the opposite. So I'll just say opposite. You just want to say that, make sure to note that the second ionization energy is always greater than the first. Always. Okay? All right, number 4, it says when an atom forms an anion, its radius increases. When an atom forms a cation, its radius decreases. Explain why this is so. Okay, so remember, an anion is negatively charged and a cation is positively charged. Okay? So when we're adding, what that means is when we're forming an anion, what that means is we're adding an electron. Okay, we're adding an electron. That's what's happening when we're turning it into an anion. Okay, and then by default, this one becomes taking away an electron. Okay, so let's think of what that means in terms of the effective nuclear charge. So if we're adding an electron, why does that radius increase? Well, we were saying, let's say we have our nucleus here. Okay, I'm just going to write the nucleus here. And we have this electron right here and out here. Let's say I add, let's say to this electron, this atom that has 2 valence electrons, let's say I add one in. So I'm going to say plus a minus, plus an electron. Well, that looks a little confusing with the math right there. So plus 1 electron. Okay, so now this becomes, here we've got the nucleus in here. Okay, and then we've got 1, 2, and 3. Okay, so now the strength, the pull that both of these electrons were feeling is now spread amongst all 3 of these, right? Now per electron, that pull is now weakened. And so what that does is it's not pulling them in quite as tight anymore, right? And so it's going to push them out a little further. It's going to make it slightly bigger than it was before. That's not another end shell. Just imagine that this became bigger. Okay, so that's why it increases when we add an electron to form an anion. Now you can think of it in terms of the opposite, where if we were to take away that electron, right, we'd go right back to here, and it would get smaller because now we're taking that same strength and distributing it amongst fewer electrons, which then pulls them in tighter. Okay, think of it like a magnet or something, or magnet might not be a good example, but like a person that's pulling, let's say 3 people, a person using a rope, and he's pulling this person, and this person, right? This is our effective nuclear charge here. If I take this guy away, now this guy who's pulling everybody now has more strength to pull on this guy and pull on this guy, so he's going to pull in tighter. So that's kind of how we think about this when we're looking at effective nuclear charge. Okay. I hope that made sense. We're going to look at how that works here in letter B. So arrange the following atoms and ions in order of smallest to largest radius. Okay, so we know the trend. So largest should be down here. So this is going to be increasing. I'll put increasing size. Let's put it on the side here. Increasing size. Okay, and then on the other direction, we've got increasing size going this way, right? Going that way. So I'll put increasing size. So now they want it listed from smallest to largest, so from this way down, all right? So we've got SN, S, SE, and SI. So this is tin, sulfur, selenium, and silicon. So I'm going to circle them, see where we are. Okay, there's that, and that. Okay, so they're pretty close to each other. So using the trend, noticing that sulfur is the furthest up and to the right, it's probably going to be the smallest. Okay, so I'm going to put sulfur first. So we got sulfur out of the way. All right, now a lot of people would be like, which way takes priority, when you're going left or when you're going down in terms of size? And in terms of the next smallest one, you would actually choose silicon, because Selenium is going to be bigger than both of them. And the reason is because selenium has another end shell, which makes it significantly bigger than both of those. So silicon is going to be bigger than sulfur, but selenium will be bigger than silicon. So I'm going to put silicon here, silicon, because it's the next smallest, and then we're going to put selenium. And then by default, we're going to put tin there because it's obviously the furthest down and to the left. Okay. All right, so letter B, we've got carbon, cobalt, chloride, and chromium. So let's circle them really quick to see where they are. Chromium, cobalt, copper, carbon, and chlorine. Okay, so I obviously noticed that carbon is at the very top, but chlorine is over here. But remember, chlorine has another end shell than carbon does. And so carbon is going to be first. Okay, it's going to be the smallest. And then we'll put chlorine. And then we'll put copper. And then this is pretty easy, right? They're all in the same line, so it makes it a lot easier. So CO and then Cr. Okay. All right, then next one, we got sodium. So Na. Na is sodium. Nitrogen and nickel and neon. Okay, so we got sodium, nitrogen, nickel, and neon. Where's nickel? There we go. Okay, so now the furthest to the left, or to the right, up in the top, looks like that is neon. Okay, neon. So I'm going to expect neon to be the smallest. Neon. Oh, I'll put just the short name. Okay, so neon. Got that guy out of the way. Now let's go to the next one. That looks like it's going to be nitrogen, right? Nitrogen. Okay, now we're debating whether we should choose nickel or sodium in terms of increasing radius, right? Which one's going to be bigger? And this one's hard to say. A lot of times we'll be tempted to go down because nickel has an extra end shell, but sodium is so far left that it is actually a lot bigger. And so we're going to put nickel first and then sodium. Okay. All right. Letter D here. We got bromine, then bromine minus, and then RB, and then I meant to put, rubidium plus here. So rubidium and then rubidium plus. I'm going to circle bromine and rubidium. All right. So bromine, we always know that the negative version, like we were talking about up there, is going to be slightly larger than the regular form, right? When we add an electron to it, we're gonna find that we have a bigger radius. So I'm going to put bromine, since it's furthest to the right than rubidium, I'm going to say bromine and then bromine minus just for now, okay? This may not be how it ends up. I'm just going to put that there for now. So then we'll put rubidium tentatively, but then we have rubidium plus, okay? Now, if you notice, rubidium plus, it has an electron configuration that is exactly krypton, but so does Br minus, right? Br minus also does. So what we have to consider then is that given that they have the same number of electrons and the same number of shells and everything, why would one be bigger than the other? And if you remember, when something is positively charged, it's pulling in the electrons with even more force, right? But bromine has less protons to be able to do that with. So bromine actually lets them loose a little bit and is slightly bigger. So this would actually go rubidium plus, and then Br minus. And then by default, rubidium, since rubidium now has the extra 4s orbital now surrounding it, okay? So kind of tricky, but that's kind of how you want to think about these. Now, similar to what we did just now, all of these electrons, if you notice, or all these elements, these ions here, they're all in what we call an isoelectronic series. I'm going to write that down, isoelectronic series. You're going to want to know what that is, isoelectronic series, okay? And what that means is that these each have the same number of electrons, okay? If you notice, O2 minus went to the neon configuration, F minus goes to the neon configuration. So does Na plus and Mg2 plus, right? So they're all at the same configuration, meaning they all have the same number of electrons and the same shells, okay? So what the only thing differing between them now is the number of protons, right? So these all have different number of protons. Now the one with more protons is going to be the one pulling in things tighter, right? It's got more protons to pull all those electrons in tighter. So we're going to say the one that's most positively charged, in this case with the most protons, is going to be magnesium 2 plus, since it's pulling on the same number of electrons with more protons, okay? It's going to be smaller. And then by default, then we'd say sodium comes next. And then between oxygen and fluorine, notice that fluorine has at least one more has one more proton than oxygen. So we're going to put fluorine next and then oxygen, because oxygen is going to have the least amount of protons, which means it's pulling on the valence electrons even less. And so it's slightly bigger with the same number of electrons. Okay, I hope that was helpful for part 1 of problem set 9.